OK, so I'm Bram Cohen. I'm the founder and chief scientist at BitTorrent, Inc. I created the BitTorrent protocol, sitting in my living room in my underwear, with no academic affiliation, oddly enough. So I'm going to talk about BitTorrent Live. So BitTorrent this is again a bandwidth-based solution. Because of the various things you could try and distribute, it turns out there's plenty of CPU, there's plenty of storage, there's plenty of lots of things. What there isn't plenty of is bandwidth. So BitTorrent's all about bandwidth, and BitTorrent Live is in a similar vein, and it's about trying to do live video streaming, like on television. Same way people still to this day consume most of their video content. And the problem here is, how do we do it peer-to-peer? How do we make it so one person can be broadcasting and 1 million people can be watching, and it all works? Well, it sounds like a reasonably well-defined problem. Here's the general goal of what you want to have accomplish. As the number of viewers goes up in a non-peer-to-peer system, the amount of bandwidth used goes up. And in BitTorrent Live, it caps out at around 10 times the bit rate of the stream, no matter how many peers you have. So in terms of where the problem is, there's CPU usage. That's not a big deal. Get your asymptotics right. I have the whole thing written in Python. It's not a big deal. Bandwidth overhead, of course, matters. You can waste around 20 to 30%. Most protocols do stuff like that. Not a big deal. Necessary headroom is a little different from bandwidth overhead. Necessary headroom includes the amount of extra space you need above and beyond your overhead in order to actually function properly. You won't be using it all the time, but if you don't have it, everything is going to fall apart sooner or later. That's generally like 30 to 50%, which compounds on top of the 20 to 30% bandwidth overhead that you have. So you're typically looking at around 100% overall combined overhead, including both. You definitely need robustness against fast peer churn. You should really engineer the whole thing from scratch to do that. And you definitely need congestion control. That's getting to be hard because you need to make it shift over quickly, which regular congestion control doesn't do at all. How many of you are familiar with TCP's congestion control? OK, you're all going to find this hella weird. Security is very hard. You need to use some slightly new-ish crypto gunk. I'll explain that. Not that weird. I didn't do it myself. And latency is the real problem. Here's the big issue. You want it to be that something is happening right now, and right now, as in about 5 seconds, everybody's viewing it, even if there's like 1 million peers. Turns out, latency is the big issue. Latency totally dominates everything. The other peer-to-peer live video systems people have made typically have latencies around, if they're really, really good, 30 seconds, more typically like 5 minutes. That's not really very live. That's more like tape delayed. Latency sucks. Latency, it's kind of like dealing with like motor efficiency with thermodynamic things. Everything adds to it. There's no cheating around it. It's this quantitative value. Everything you do adds to it. There's no way of just throwing an asymptotic and stop worrying about it. All of your constants matter. It's horrible. All right, so this is generally the overall architecture. There's an input camera. It does something to the origin server, which speaks RTMP to what I'm calling the source, which is one of my servers. Those speak BitTorrent Live protocol to all the peers, which then speak RTMP to a Flash player in a web browser, and then it gets displayed. Reasonably straightforward architecture, integrates with the web. My goal is to make it so someone, once they've got it installed, doesn't know they're using it. They go to web pages that use it. It plays. They don't know the difference. Kind of like Flash in general. Yes?
Does it have to be a Flash player?
No. Well, in theory or in terms of actual practice today?
Both.
In theory, no, not at all. I don't really care. In terms of actual practice today, you're basically stuck with H.264 on Flash if you want consistent playback everywhere, because Flash is the only thing that's widely available. The general pissing matches around licensing of H.264 and its inclusion in HTML5 resulted in this wonderful thing of everyone being free of their dependence directly on H.264, and instead they're dependent directly on Flash. Thanks, Google. All right. So in terms of basics here, the broadcaster that was on the origin server, they use any encoder that they want, flash media live encoder, open broadcaster, XSplit, Wirecast. These are all things that we've seen people use. Hopefully it uses X264 under the hood. X264 supports VBV. VBV means that you can actually control the bit rate in a reasonable manner. Spikiness in bandwidth is very bad for this protocol. It's just a bad thing to have happen because peers adjust weirdly to it. They don't quite know what to do. Even in theory, even if my protocol was better at handling it, it would still be a major problem. You don't want, when something's kind of running at the limit across all peers, uploading as fast as it can for there to be a sudden spike. It'll overload it, and it's very hard to get out of a bad situation once you're in it. Of course, most things do use X264. Most things don't actually have any pass-through of the parameters to the encoder to actually send to the X264 implementation that they're using. Thanks, guys. Real helpful. Of course, we send to the sourcing application via RTMP. And I personally have essentially zero interest in video codecs. So I treat the data as a black box. And I take each packet, and I remember the contents of that packet and the time that I got the packet, and I resolve to try and replay that as exactly as I can on the playback side, albeit delayed somewhat. All right, so there's this series of steps that you need to go through in order to do streaming. And I'm just going to follow like the life cycle of a packet here, more or less. So first off was encoding. I just covered that. Next, you need to batch up your data and sign it. So every quarter of a second, you take all the data that you have and batch it all up. You compact it into a bunch of packets, like you see in this diagram here. Each one of these here payloads would actually potentially have multiple RTMP payloads inside of it that it spans, and they're all just designed to be about the same size, just a little bit less than an MTU. And then you use a hash tree, like you see here, binary hash tree, and sign with ed25519. That makes it so you've got, in each and every packet, you have 64 bytes of overhead for the ed25519 signature and 12 bytes for each level of tree. I just kind of decided to truncate my things in the middle here to save myself a few bytes, because this is overhead for every level of tree for every single packet. So in principle, I could have gone a lot less than that. I was a little worried about blah, blah, blah attacks. I just decided on 12, and someone's going to scream at me no matter how I truncate that. So that was the value I used. By using this combination of things, I managed to make it so that I can actually literally sign every single packet that comes through and still not use a huge amount of bandwidth overhead. But I did, in fact, need to use ed25519. And I still haven't switched to SHA-3, which I really ought to do. Yes?
So what does the percentage overhead end up being?
The percentage overhead of bytes on the wire is, let me see. It sort of depends partially on whether you include the like UDP overhead as well. So that's like 28 bytes, and there's 64 bytes. You wind up with roughly, let's say, 100 bytes of overhead, and MTU is like 1,200 bytes plus. So yeah, a little less than 10%. You have bigger issues with just necessary headroom that you need. But the overall overhead is quite under control here. Actually, CPU is a little bit more of an issue. I did, in fact, have to use ed25519. I'm not just being goofy for that. And I'm switching it to use the Ref10 implementation, because half my CPU is going to ed25519 right now. You know, you verify signatures on every single packet. It's, yes.
You ever try using GPUs to accelerate it?
I don't have control of the machine. My software needs to run on every random bit of garbage on the internet.
Okay. Flash. Flash.
Oh, well, Flash isn't doing that part, but this has to run on like mobile phones and different architectures and blah, 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 blah. I'm stuck with the garbage I'm given. I have these home net connections where people are running other applications behind the same net connection, and they're on Wi-Fi that has a high failure rate. I'm stuck with the garbage. It's my problem. See, the thing is, packet-based networking is the absolute worst form of networking except for all the others. Like no one in their right mind would actually design global communications with no concept of connectivity or guarantees or anything like that built into it whatsoever. But it turns out the best way to actually build the network is to build it in exactly that way, with the assumption that some engineer will figure out that problems. That some engineer would be me over here. There's while I was working on this, someone asked me at one point what my approach was, because I was claiming kind of ridiculous benchmarks, which I can actually demonstrate in the wild now, by the way. But I was claiming kind of ridiculous benchmarks. And so he asked me how my architecture worked, because he was saying you can't possibly have less than a 30-second end-to-end delay. And he kind of had a reasonable rough sketch of why that was. I'm like, well, you're making assumptions here in your model that aren't true of how I do things. And he asked me what I meant. I'm like, well, can you name a protocol that has high robustness and low latency? And he didn't know what I was getting at. And it's like, well, I didn't say that it needed, efficiency or congestion control. So if you want a protocol that has high robustness and low latency, and its overhead isn't really all that bad either, you have this protocol where every peer has three bidirectional connections to other peers. And every time it gets a piece of data from one peer, it sends it to the other two if it's never seen it before. This is what you call a screamer protocol. It has 100% overhead. It has no congestion control. However, very high robustness, very low latency. Works great. So my idea here, my secret sauce, just about the most embarrassingly stupid piece of secret sauce I've ever had in any project I've ever done. My secret sauce here that I thought of in 2008, which was actually the thing that got me thinking, hey, maybe I could make a live protocol. This was literally my big idea, was, hey, I know, how about I scream the data out to, 10% of the peers, and then do something a little more controlled to the rest of them. And that way I'll get the high robustness and low latency of a screamer protocol while keeping the fact that it has no congestion control, and it has high overhead under control by only doing it for a small fraction of all my traffic. This was my big idea. Because it was very obvious to me that tree-based protocols were not going to work. Just the way the failures cascade is just not happening at all. I don't know why this was so obvious to me and not anybody else. But it wasn't. Anyway, my idea here is to combine the best aspects of a screamer and a tree-based protocol, which is what I've done. So first of all, you scream data out to 1/6 of the peers. So turns out you scream to more than 10% of the peers. You scream to like 18% of the peers, or 1/6. This is what happens. There are 6 what I call clubs. So every piece of data has a sequence number. If you want to know the club associated with that piece of data, you take the sequence number modulo 6. Every peer is associated with a club, basically assigned randomly. When you check in with the tracker, there's a BitTorrent style tracker. It'll suggest a club for you. It just rotates through them, increments over the last one it suggested to somebody. Try and get reasonably even distribution. Doesn't really matter all that much. So, so you have the source, which is a member of all clubs, unlike every other peer, which is who are members of exactly one club. If you read the patent, it'll say every peer is a member of 2 clubs. Don't worry about it. But the peers then scream to each other, and then for the last hop, and only the last hop, does it send in a more controlled manner, and 5 out of the 6 peers get it that way. A little less, because the source sends to a bunch, but tiny amount less in a very big swarm. Okay, any questions about that? Everybody get it? Okay. All right, I said that. Oh, okay. So there's this big difference between the last hop and the not last hop. In terms of prioritization, if you're familiar with BitTorrent protocol, most people who are familiar with the BitTorrent protocol, their intuitive notion of prioritization is you should ask for the rarest piece of data first, because that's the way BitTorrent works. And that approach does, in fact, work. It does, in fact, get the data out there. However, it's horrible for latency. When you're worrying about latency, there's a very, very big difference between it being the last hop and being not the last hop. If you're going to send data to someone who is a last hop, you can send it kind of at your leisure, and it's not going to make a big difference. It's only going to increase latency for just them. If you're sending to somebody who's not the last hop, if you delay it, not only are you delaying it for them, you're delaying it for everybody they're going to send it to as well. So from a latency standpoint, you really want to send the very most the very most urgent stuff first, always first. And then you want to send it first to the peers who are going to rebroadcast to somebody else, and then finally to the peers who aren't going to rebroadcast to anybody else. That way you optimize your latency. In principle, you could have some concept of how many hops each peer is going to send it to. I make no such distinction here. I just go last hop, not last hop. Yes?
I'm not quite getting this. That's a small size picture. It fits on the screen.
Yeah.
What's it look like if I've got 1,000 nodes?
Well, first off, if you have 1,000 nodes, there are going to be a little less, around 180 peers in this group here. And this is there are 6 of these overlaid on top of each other. So this is a subset of all connections, just the ones relative to one particular club. So when you're looking at just one club, there's around 180 peers here, 1/6 of 1,000. And there's the source, which is connected to like 3 of them. And these have a pretty random graph going between them of where everything's going, but it's densely connected. And then the remaining 800 some odd peers are all down here. And the average fan out from these peers here to the ones down here is 5. And each peer here is getting data from exactly one of those. But the number of these connections going out from these is highly variable, because that's how the congestion control works. I'll get to that in a second. Does that make sense?
So there's some scaling limit based on how big the blob in the middle there gets?
No, there's no scaling limit. No, the blob in the middle increases as the number of peers increase. It's always 1/6 of the peers. Each of the other peers down here is a member of another club. So I'm only displaying 1/6 of the total connections in the whole thing right now. And for each of these peers down here, they'll be a member of the big cluster for a different club. Does that make sense? It's general.
The maximum depth of the center club grows very slowly.
The
maximum distance at any packet.
Oh, yeah. The depth that you go is going to be basically exponential. Is logarithmic, sorry.
Yeah.
Because this is a screamer protocol here, you get this exponential fan out in here, and then a factor of 5 for the last time. Is that making any sense? You look kind of confused.
I don't understand it well enough to explain it to somebody yet.
Oh, okay. This is actually kind of a simplification of the overlays concept, which is used in other live protocols. So there's this invariant within your group that's screaming here. By the way, these connections are all directional. There's no bidirectional connections here. If I'm sending you data, you're probably not sending me back the same data, even if we're both in the same club. Just a thing to know. So there's this question of how is the graph in here formed between these peers. First off, every peer has at least 2 incoming and at least 2 outgoing connections, because 2 is the number after 1. And you need that for exponential growth. I at one point had this as a strict invariant, that every peer had exactly 2 incoming and exactly 2 outgoing. This resulted in state machines which were really scary rocket science and could never quite work exactly right due to edge cases of peers leaving. Eventually, I came up with this brilliant idea that peers were allowed to have 2 or 3 incoming and 2 or 3 outgoing connections. And this resulted in the state machine where if you had 2 or less and you get a new one, you just accept it and keep going. Anybody care to guess what happens if you have 3 connections and you get a new one? What you do is you pick randomly one of your existing old connections and you drop it. This can potentially make it so that the peer that you just dropped a connection from is now below their limit. They'll go find a new one. and form a connection to them. That peer might then be above their limit. This can cascade a little bit, but because there's slop, sooner or later they'll hit someone who had extra slop already available, and the chain reaction will stop. Kind of a stupid idea, but it works. Did people find what I just said really confusing, by the way? Was that weird? Like, that, pretty strange? OK, sorry. All right, now, so after you're done screaming, you need to send out data in a reasonably coherent manner to the last hop. TCP is congestion window-based. I hate congestion window-based protocols. I think it's a horrible hack. I really like pacing out my data carefully. When you're using a congestion window, you inherently have this problem that you might, maybe, be sending all your data as one giant glop every RTT, and then your queue in the middle has to have an RTT's worth of buffer available in it, and it's just horrible. And aside from that, all my congestion control here is based on one-way delays, not packet loss, and that really gets messed up when you aren't pacing out your data carefully. So I pace out my data, meaning I send a packet at regular intervals. Because this data is kind of known data, I actually know what its bit rate is. The source just says what the bit rate is in every single piece of data coming out. I don't need to guess it. I don't need to adjust for it over the time. I just say it, and I follow it. You, of course, take the overall data rate, divide by 6, because each connection is for 1/6 of the data, and you multiply by the number of upload connections you have. That's the rate at which you send data out. So then you calculate your pacing delay, which is if I didn't get any new data coming in ever, how long would it take for me to send out all the data I have currently queued up to send out? And then you increase your pacing delay. You increase the rate you're sending if that data isn't, if the pacing delay isn't 0, based on this here formula. This is an important formula. Whenever you have control loops, and I have a lot of control loops in this protocol, by the way. I've learned way more about PID controllers than I ever really cared to. In general here, I'm doing what you call I controllers, meaning I'm doing it based on a lot of aggregate data. So you're currently looking at your current pacing delay is very much an I controller. You don't really ever want to rapidly change the rate at which you send data out because it'll mess up your own congestion control really badly. You definitely don't want to ever send at very much more than 25% the rate you really should for 2 reasons. Number 1, because, again, you'll screw up your own congestion control. Peers will stop downloading from you when they shouldn't because you're uploading faster than you really need to. And number 2, there's this subtle, complicated thing where if a peer doesn't have enough download capacity, it needs to quit eventually. So the thing that happens here, this is kind of complicated and subtle, is if I'm uploading to you and you have insufficient download capacity, I'm going to keep just trying to resend everything that I'd sent to you already, and all these are going to keep getting redropped because your download isn't capable of handling them. Your backlog is going to keep getting bigger. I'm eventually going to start sending at 25% faster than I really should be, but no more. And you're going to keep dropping data, and you're going to keep falling farther and farther behind. And eventually, if you fall too far behind, you give up and leave the swarm. And that's how peers figure out that they have insufficient download capacity. Kind of a hack. Well, I mean, it works. Yeah. Anyway, this is the way you keep this from oscillating. That was a lot of work.
Down to another peer?
No. When I say a peer doesn't have sufficient download capacity, I mean the size of their download pipe isn't enough.
Okay.
For the bit rate of the stream. There's no like saying I'm just going to use a fraction of the bit rate of the data stream here. Either you can play the whole thing, or eventually you just kind of give up.
Mm-hmm.
Yes.
Yeah, 2 key questions. So why do you say screamers?
Screamers?
Yeah.
That's the technical term for it.
Technical term, right?
Yes.
Can you say like a broadcasting or something?
I don't know. I like the term screamer.
And secondly, how did you find the magic number 6?
I pulled it out of my ass. If ever, I'm good at coming up with magic numbers. I have a lot of fiber in my diet. If ever you're doing your own protocol and need some magic numbers, you can come to me. I'll help you. I'll hook you up. Actually, I determined it via simulation. I have this whole tricked out system where before I actually made my code work, I wrote an emulator for the internet. It turns out I spoke previously about how bad it is to do this. Whatever. Anyway, I made an emulator for how the internet works. It turns out it's hard to simulate TCP because TCP stacks are different everywhere. It's actually very easy to emulate router queues because they're very simple beasts, unless you're trying to get fancy and do red or whatever the fancy tail drop fanciness du jour is these days. I'm against that stuff. It makes me not know how the internet works. But router queues are very, very simple beasts. Things get delayed in transit between peers. When something hits a queue, it gets added to the end of a buffer where everything is shoved out of on a very regular schedule. If the new packet coming in makes the buffer too big, it gets thrown out. That's how the internet works. So I wrote an emulator for that. And then I made it so all of my code has these funny things where I have this call called det shuffle for deterministic shuffle, where every time I iterate over the keys in a dictionary, where the order in which I iterate over them matters, I first sort and then randomly shuffle the order of the keys so that I can run my emulation over and over again, and it does the exact same thing every time. Yeah. And it was in these emulations that I just played around with the magic numbers and came up with that as a value. There are some trade-offs to it. If you have a very, very large swarm, it's kind of good to make it bigger because that makes your overhead be lower. And if you have a very, very small swarm, it helps to make it smaller so that there's more offload to peers, but that makes your overhead larger and makes your congestion control work worse. So 6 is pretty good on basically all sizes. It's really nice, by the way. I highly recommend this having an emulator thing. I was able to actually run things and figure out my overall architecture before I'd really written much of anything, like actually something that spoke UDP, or even actually I'd figured out my congestion control, or for that matter, on my to-do list in 2009, top of the to-do list was remove psychic powers. Because I hadn't actually figured out my whole protocol yet. And so there were places where peers needed to find a peer, so they just went and looked in the global data structure of all peers and picked one. You had a question?
I was going to ask, how big is a big swarm?
That's kind of a relative concept. There are a few different scales where things start to behave a little bit differently.
Okay.
When you have around 10 peers, you've still likely got most of your data, or maybe like half your data coming off the source. When you get up to 100 peers, you have most of your data coming off of peers. When you get up to around 1,000 peers, you get this phenomenon where when a peer is doing peer gossip to find potential peers, it no longer finds out about almost all of its potential peers that it could be using, and that affects the congestion control in subtle ways that I'll get to. And then above 1,000 peers, it's all kind of the same. You can't tell the difference. Yes?
You said at the very beginning that you had one advantage, that you knew the bit rate at the beginning. You knew the bit rate up front.
Yeah.
Yet that the bottom peers were being booted because they couldn't support the bit rate.
Oh, I don't know their
discovery.
download capacity.
Right, but okay, so that's how you're measuring download capacity and comparing it. That you can't just notice that.
No. These are peers on the internet. I don't know anything about them. They have shitty CPU. They have unknown data
They're
connectivity.
receiving packets at a rate that they can measure.
Well, you can look at your data rate coming in, but
Yeah.
how do you know whether the problem is the peers sending you data or you're receiving data? And how do you know if the problem's transient or not?
Yeah, okay.
And all that kind of stuff.
But you do know the rate that you should be getting it at.
Yes. But that's about all you know. There's all this, like, in almost every case here, you can say, oh, well, here's a heuristic which will really nail it. But the problem is that heuristic only really works on a clean network where nothing bad is happening. In Bram worlds, bad stuff is happening all the time. You just have constant peer churn. You have constant congestion control happening. The world is out of control. I don't know like what the I don't know what the transfer capacity of these peers is. They don't really have great CPUs. They have crosstalk going over the same things, which might or might not be transient. I don't know what's going on with these peers. Yes.
How fast does peer churn occur?
Very, very fast.
So fast.
Okay, I said you're all going to find this hella weird here. So now you want to do congestion control. So first off, don't use pipes. TCP inherently, anything vaguely TCP-ish has this concept of a pipe. I'm sending you data. I try to send the data. If the network isn't ready for the data because I'm sending it too fast, it backlogs it. That's not happening here. I need low latency. That abstraction fundamentally introduces a lot of latency having nothing whatsoever to do with the network. Don't use it. Can't use it at all. All right. Well, that kind of blows anything vaguely resembling TCP's congestion control right there. The fundamental construct here is whenever you get a piece of data that's delayed too much, by the way, means 200 milliseconds. You send a FOAD message to the connection, to the peer that was sending you the data. FOAD is this universal term for terminating a connection permanently. It's an acronym. It stands for fuck off and die. This is an actual technical term. So you send a FOAD message. No, you do not. So the way this works. Well, the peer that was sending the data might have a backlog in their outgoing queue, which is going to cause delays for a whole lot of peers, and it's very important to get rid of that. More important to get rid of that than to get your own data quickly. At one point, someone new to my team, someone joined my team right when we were switching to monotonic time. By the way, don't use anything except monotonic time. This person who is new to my team and kind of a junior coder said, well, why don't you just make sure the machine's running NTP? And I said, okay, you're not allowed to ask that question ever again. There's this myth that there's this thing called time, that there's this global time that's accurate everywhere. It doesn't exist. In my entire protocol, there's only one place where I call true time, and that's just to make it so that if you have multiple sources, they can kind of compare to see which one started later, so the one that started earlier can go away. But everywhere else in the entire protocol, I call monotonic time. I have no concept of what the actual time is. The only thing I know is that there are clock skews between machines and delays. And so if I'm sending you data, you can look at the data that I got sent to you, and it'll have some delay. The delay might be 3 years and 5 months. Which is not necessarily a useful piece of information, but if I later on send you data which has a delay of 3 years, 5 months, and 100 milliseconds, you can go, oh, that's 100 milliseconds more than before. Maybe there's some noise in the network here. And then if I send you one that's got a delay of 3 years, 5 months, and 300 milliseconds, you go, oh no, that's horrible. That's too much delay. I figured out some tricks here for dealing with time. Time sucks, by the way. Hate dealing with time. Spent way more time dealing with time. I never really cared to. In general, a basic trick you should know, if you ever have to deal with networking and sending timestamps over the wire, the appropriate way of doing it is whenever someone sends you a timestamp, the way you send a timestamp is it's 2 bytes, which is in milliseconds modulo 2 to the 16th. For every single connection or every single peer that you get a timestamp from, what you do is you look at the last time they sent you a timestamp and what you thought their time was, and what their new timestamp is now, and you kind of guess about what the timestamp should be given the current thing, and you find the nearest value modulo 2 to the 16th in milliseconds that should be. This results in this very nice behavior that your assumed time from a given peer at first is something close to 0, and then it kind of just gradually increases over time in about lockstep with you, and you don't get any thresholding thing where you're flipping back and forth between two values and suddenly jumping 2 to the 16th milliseconds or anything like that. 2 to the 16th milliseconds is almost a minute, fine for my protocol, because timeouts are way quicker than that. Anyway, just so you know, that's the right way to do it. OK, so the way you find a new peer. You send messages to all your current peers saying, hey, tell me about everybody you know in this club. They send you lists of everyone you know. They also help you out with some NAT traversal. They have active connections to these peers. They tell that peer, hey, send a ping request to this person to poke open a hole in NAT. Turns out enough peers are either behind open NAT or have UPnP running that this works great. You then pick which one to download from using this highly sophisticated technique of picking one randomly. I tried to be more clever about this. And in general, whenever you're working on heuristics, whenever you think you're really smart and have come up with a heuristic for something, it's always very, very important that among the heuristics you're testing out, you try the exact opposite of what you think the right thing to do is, because that's frequently correct. This was one of those cases. The behavior here is not terribly obvious. Let's take a very simple model on the top here, where you have a peer, and it's sending out data to its peers. And whenever a peer gets a list of peers, it just picks a random peer out there in the swarm to start downloading from new. And then the way the congestion control works is every time a peer comes to its full capacity, something really horrible happens, and it drops every single connection out that it actually has. In practice, it's not quite that bad, but this is a reasonable first approximation of what's going on. Then you get this pretty predictable behavior where regardless of the utilization, or regardless of the peer's upload capacity, you get the rate at which the peer is sending, uploading, increasing linearly until it hits 100% and then drops down to 0. Now, what do you notice about the integral of this curve? It's 50% of the potential capacity. That's not really all that bad, actually. That's pretty good. In practice, when you have a large swarm and things aren't working quite so horribly, what tends to happen, and again, I'm being cartoonish here, is just due to an artifact, you asked what's a big swarm, and I said 1,000 peers. Peers wind up not knowing about every other peer every time they do a thing. In very large swarms, the peers that have more connections will tend to get downloaded from more, just because when you're asking for the total list of peers, they come up more often. There are various hacks that could improve this. They would likely screw things up on small swarms. I haven't really messed with trying to fix it all that much. And let's say that your increase in rate, instead of being linear, is a little more exponential. And then when you hit 100%, it drops down to, let's say, 50% instead of 0, because it doesn't drop every single connection. Some of them drop, and they drop quickly enough that the remaining ones don't drop. And so this is more kind of what you get. And this is more, the integral of this is more like 3/4. The remaining stuff here is kind of necessary headroom. Not doing too badly, actually. So that's how the congestion control works. Yes?
If you're collecting this list of peers, how big an impact on the bandwidth is that?
Nothing. You have like, on the order of around 10, maybe 15 connections to peers. You send a message to each of them asking for all their peers in a club. They all send responses. You send pings to all those. So that's around 100 packets with around, 30 bytes each maybe. So that's 3 kilobytes total for finding a new peer. Not a big deal.
If you're going to pick one randomly, why do you ask the peers for their full list connections instead of just saying, why don't you pick one randomly and send me one? You get 15.
Oh, because you don't know if
You
don't know if you'll succeed in pinging them.
You don't know.
You don't know if you'll succeed in pinging them. You do ping all of them yourself. To make sure that NAT traversal is working, to make sure that they've been up
Okay.
reasonably recently.
Okay.
And also,
You'll
and-
pick one randomly. If that one doesn't work, you'll work off that list.
yeah, that would be more. You could try and optimize this a bit, but that would be
Yeah.
more round trip timey stuff.
Right.
You could just use the very first one that you got, but that would tend to bias towards particular peers that have low
Right.
latencies and stuff. I suppose I could make it so that every single peer you go to would only send you a single one in response. That wouldn't really fundamentally change how the overall protocol works, though, just because in the case where you only wind up getting a few peers in your responses, your overall behavior is going to be the same anyway, and you're going to have to wait the same amount of time before picking one. So,
How long average does it take you to get that list back?
oh, it just waits a second before picking one.
Okay.
So it doesn't have any concept of checking to see if it's gotten all of its responses. It just waits a second after it's started the whole process before picking one. And if it doesn't have a list of them, it just starts the process over again at that point.
Okay.
This is, in many ways, not a very sophisticated protocol. It's all hacks and emergent behavior. Okay, now you need to prioritize your data. Like I said before, you want to send your in-club data first. So let's say that you have 6 outgoing connections, and this is saying what pieces of data the peers need. These are the latest piece of data you've gotten, and these are earlier pieces of data, and your in-club peers already have most of the data. Your out-of-club peers don't have quite so much of the data. And the order in which you send data to them is the order in which I've numbered here. You round robin between peers. The idea being that each peer should keep the current latency that it has. If one peer is playing with very low latency, you want to send it stuff relatively quickly. If one peer is playing with high latency, it's okay to take longer to send it stuff. Round robining peers preserves that across peers. And of course, you send the earlier data first. And, wait. Oops, sorry. And well, that's what you do here. So you see it goes, I've numbered them, 1, 2, 3, 4, 5, 6. Just sticking with in-club and round robining. And then it goes to the out-of-club and goes 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Reasonably straightforward. Of course, it's unlikely that you would go that whole entire time without getting any new data in, but that's the order you'd go if you never got any new data the whole time you're sending those out. Oh, by the way, I didn't do these beautiful diagrams. You might have gathered by my difficulty of setting things up. I don't really do AV at all. Some people I work with decided I should have better presentations, so they insisted that I scrawl some diagrams, which actual professionals who I work with made into these very pretty diagrams you see here. They should be iterated on a bit more, but thanks to Taka on my team for actually making this look nice. There's an exception to this. You get this case. Again, this is something that I found in the emulator, which was hard enough to find in the emulator and would have been a real nightmare to try and find on a running system. You can get this interesting phenomenon where the source only has one out-of-club outgoing connection, and that outgoing connection gets starved out. This can be very, very bad, because that one peer is just going to not play ever. So to get rid of that problem, you have this exception where you make sure every 10th packet is out of club. So this is a case here where you have just the one out of club connection. And you see it is round robining in club, but after it gets to 9, it just sends number 10 out of club. Just literally, if it just sent 9 in club in a row, number 10 goes out of club, and then it goes back to normal prioritization. Kind of a hack, it works. Prevents some really bad starvation that could happen. In case you're wondering how I got the every 10th packet, same thing as before. I did actually test it and wound up using 1 out of 10. I'm pretty good at that little game of making up numbers. Yes?
Do you just happen to get up early in the morning, have breakfast, and notice these things, or you have some way of more systematic way of finding them?
I run emulated tests. which display.
Eyeball them.
Yes, I eyeball them. They have all kinds of numbers that they spit out and stuff as they're running, and which is utterly inscrutable to everyone but me. And someone on my team is actually adding headers and stuff to label what everything is, so you can see what's going on with that. And I notice bad things happening. Like I'll just run a simulation and notice that, really an emulation, because the peers don't know that they're in a computer. I'll notice that like one peer has very high latency, or that one peer quit, which didn't make any sense because there's plenty of bandwidth, or it seems like there should be plenty of bandwidth. So long, oh, well, what if I increase, so there's plenty of bandwidth for everyone, and then it still happens. Oh, how'd that happen? I start running it. Or sometimes I'll have something which only happens in one run, but because I have this magical deterministic emulation, I can do that run over and over and over again and really figure out exactly what's going on. That's how I find this stuff. I find the thought of trying to like do this without that like nightmarish, horrifying. I would never even try. Yes?
Is this a good time to talk about clubs and your design for them, or are you going to hit that later?
Clubs? I talked about clubs already.
Mm-hmm. You said, like, these guys are in one club and there are other clubs, but you didn't really talk much about
There's 6 clubs.
clubs. Oh, okay.
That's it. Every peer is a member of one club.
Okay.
That's all there is to say about clubs.
Okay.
When a new peer comes in, it picks a random club to be a member of.
Okay.
In order to try and make it so that there's approximately equal numbers of peers in every club, the tracker will give a hint. The way the tracker gives a hint is it takes the last hint it handed out and adds 1 to it.
Okay.
Okay. Finally, you reconstruct your data and play back, which is kind of a trivial thing. Well, actually, no, it's not trivial at all. It's horrible. This has a lot to do with time again, and local CPU delays, and who knows what. So to first approximation, you don't do skips ever. Just you get data comes in and you play it out. If the next piece of data that you're scheduled to play isn't here locally, you wait for it and then you play, and you reset your delay to now be based on how long it took for you to get the data. So that's your new latency. You, of course, can't do that at the very start. You need to decide when it's OK to start. This is how you decide when it's OK to start. I don't know if you can see, I'm numbering the packets from the upper left, just counting in read order down to the lower right. This is typically the spread of packets that you'll get. You're downloading from peers who start sending you at differing points. They send you everything sequentially. You get these kind of vertical stripes of stuff. As soon as you have 6 contiguous packets, in this case it would start at 78 over here, because 78 through 83 is 6 contiguous packets. You start playing there. That's where you start your reconstruction. And then you start playback. I hate CPU delays. Whenever you get data, whenever you wake up from a sleep, you don't generally wake up when you asked to. You wake up later. Sometimes you wake up earlier, especially in Windows machines. Anyway, I'm not kidding. You always remember when it was you were supposed to wake up. So you wake up to send a piece of data. You just send the piece of data out for playback, and then you schedule the next piece of data to be sent out. But you schedule it when it was supposed to happen, not based on the delta in time from the current one to that one, because you need to correct. For CPU delays, there's a very, very big exception to this, which is if you didn't have any data to send out before, and you do now because you'd caught up, then you send the next piece of data, because you were waiting for the next piece of data. You then send it out immediately and set the playback delay to be the current delay based on that one piece of data. CPU delays be damned. It took me way too long to figure that out. That's the right way of doing things. So you can't completely get away without having skips forever. You do occasionally actually lose a piece of data. and just no amount of just waiting for it will make it come in. To account for that, if you are frozen, that should say frozen rather than delayed, but if you're frozen for more than 2 seconds, you go into desperation mode, which basically is the mode that you started with when you first started playback in the first place. And occasionally you can run into a situation where you got delayed a large amount at some time in the distant past, and and you continued playing at a high delay ever since then, and it seems like it's not necessary anymore. You don't have any terribly good options here. You can keep playing at a high latency forever. You can skip a couple of seconds of video, or you can play back sped up. I play back sped up. Currently set to 10%. I should probably change it to 5. All right, finally, after that thing, that, by the way, had to do with what I call the smoother. I hate working on the smoother. It's the most hated part of my own code base. Finally, you wait for a keyframe. I mention this because it sucks. Keyframes are typically, people don't like putting keyframes in their video because it hurts the compression on their video, as a result of which you will typically get keyframes every, 8, 16 seconds, which will result in waiting for a keyframe to do your playback. Like literally, my protocol is working great. It's getting the data, it's ready to play the data, it's sitting there waiting for a keyframe. So it takes like 8 seconds to start playback, and the user thinks it's playing with a delay of 8 seconds. No, it's playing with a delay of 3 seconds. I just had to wait 6 seconds for a keyframe after I actually started my playback. It sucks. This is kind of a deep problem in general. It's the reason why changing channels on cable sucks, by the way. They don't like sending keyframes either. They do send keyframes every second, just so that it doesn't just freeze every time you change channels, because they have this problem too. But when you're just flipping channels, you definitely notice it. That's why it takes longer to change channels now than it did 20 years ago, in case you were wondering. Latencies in general have slid backwards horribly across the board. People interrupt each other on the phone all the time these days, and it's not that people have gotten more rude. Oh, I suppose they probably have. It's because the round trip time on phone calls has gone up. It turns out a round trip time of 1/3 of a second on a phone call is kind of manageable. Turns out, by an interesting cosmic coincidence due to the speed of light, you kind of need close to 1/3 of a second RTT on a phone call if you're going between New Zealand and Spain. I think they should just plumb a line through the center of the Earth. I'm told that's got some engineering challenges to it. But even if you're in the same city, see, the telcos decided in their infinite wisdom that 1/3 of a second was acceptable, or 1/3 of a second was good. 1/3 of a second is not good, okay? Like less than 100 milliseconds for a human voice call, kind of okay. More than that, it starts getting annoying, and 1/3 of a second is like just on the edge of totally and utterly unacceptable. So if you notice that whenever you talk to people on cell phones, and they're on cell phones, which is every call ever these days, even when you're in the same city, you have this horrible round trip time on it, and you'll be interrupting each other all the time because you stop talking to give the other person a chance to talk. You wait 200 milliseconds, which is plenty of time for them to respond. They haven't responded yet because they haven't heard you stop talking, and then you start talking again, and then they start talking over you, and that's why people interrupt each other on calls all the time. You notice this at Ma Bell Park. I don't know what it's called these days. It's obviously Ma Bell Park, so I'll just call it Ma Bell Park. If you're watching the game and watching one of the videos they have there will be a video of the game that's happening 100 feet away from you. It's delayed by 2 seconds. Right there. It used to be you could sit in a baseball stadium. Not that I watch baseball, but you could sit in a baseball stadium, and if you were sitting back in the bleachers, you could be listening to the radio, and you would hear calls on what was happening in front of you before the sound of the play got to your ears, but after you saw it visually, because it turns out the speed of sound isn't really all that fast. And it's quite noticeable when you're in the back bleachers. That trick don't work no more. It turns out if you really, really want to optimize for latency, well and truly, like, optimize for latency across the board, you basically go back and build the same shit that we had in the 1950s is the way you optimize for latency everywhere. Just no processing in the middle of anything, no compression, no nothing. Just straight through analog, gets great latency. Also really good if you want space aliens to be watching your TV programs. Very, very hard for space aliens to see anything if everyone's getting it over their local wireless, because it's not loud enough for them to see on their giant telescopes. Anyway, that's enough ranting about delays. So it's a problem for changing count, and that's all I had to say, actually. So that's my talk. Does anyone have any questions?
Like about talking about like this more in depth.
No.
Fine.
This is as much as I've put together on it. I will put together more in the future. I'm also planning on making the code base available for the purposes of academic study. There's a patent. It's half right because it's kind of a moving target, and it's written kind of in patentese. But what you just saw is about as much information as is generally available now. So if you have any questions, you can ask. Yes?
Instead of that paper,
Yes.
why not the other paper? Because you kept dropping in these little, this is what you think you should do, no, do this. Instead of doing a paper on this, do a paper on how to do this.
I'm not sure what you mean.
Well, you said, okay, I build an emulator of the internet.
Yeah.
And study it. Always try the opposite.
Yeah.
All those things. That's far more useful than this.
Okay. I guess.
It's more fun.
Yeah, the emulator is with my code base, actually, and it is a really dumb piece of code. And people who actually know how the internet works cringe horribly when I tell them the model of the internet in Bram world. But see, in Bram world, the backbone has infinite capacity, and your latencies come from a few places. There's pacing delay on the actual peers because it doesn't send out data just because it doesn't feel like it, because it's running Windows, because I don't know, it doesn't send it out for a while. And then you have queuing delays on the router, which data gets to basically instantaneously, which can be like a couple seconds long, and there can be buffer bloat and yada, yada, yada on that. And then once data gets off of that, it has a little bit of serialization delay going out that's very small. And then under good conditions, most of the latency comes from the next thing, which has to do with the speed of light. Everyone just kind of assumes that there's all this delay in routing. Turns out it's not. Well, delay in routing is in microseconds. Delay due to the speed of light is in milliseconds. The speed of light isn't really all that fast. If someone can figure out how to make the speed of light just like 1 order of magnitude faster, it would really make my life a lot easier. Either move everyone back onto the same continent or make the speed of light 1 order of magnitude quicker. Would really just eliminate a huge number of engineering challenges for me. And then you hit another queue on the receiving end, and then someone plays. I think my emulator doesn't actually emulate a queue on the receiving end. It just assumes they're all super fast. Anyway, in Bram world, the backbone internet capacity is infinite. So, yes. Or here, you.
Is this protocol open?
What?
Is the protocol open? Like, could I write my own client?
No, it is not.
Not?
No, I'm gonna. It wouldn't really do me any good. In practice, these things tend to be dominated by one implementation anyway, and I really want to maintain the ability to rev it over time. And also, unlike BitTorrent protocol, this isn't really that resilient to peers being misbehaved. So it's pretty easy to write a peer that just doesn't really behave all that well and kind of screws up things for everybody else. So I want to maintain a certain amount of control over the whole things. Yes?
Have you tried this on large networks like 10 million?
Not 10 million. I've tried it on thousands. We've had networks of thousands of actual peers in the wild actually watching something of their own free will. We also ran a whole bunch on EC2, which is kind of an artificial situation. I think we only got up to like 8,000 peers on it because we used all the available EC2 instances at that moment. But that worked. We were able to get that to work fine as well. That was also a very useful form of testing to do. But yeah, we've gotten up to a scale where I don't anticipate any changes as it gets larger, really. Yeah.
You tried comparing it against other products like StreamTorrent and Beetle and other.
Yeah, they're not even comparable. It's a blowout. Yes.
Do you have any plans to use WebRTC?
What is WebRTC?
It's just like peer-to-peer thing in the browser. It's a new web standard.
For
Not
streaming
roulette without
video
Russians,
and
yeah.
audio.
Video conferencing.
That stuff isn't really useful for me because that's for like point-to-point video, and I need actual connections myself. I basically need to be able to send UDP traffic. If I can't actually send UDP traffic, I can't do my protocol. Yeah.
How much of your model assumes it's okay to lose content periodically, and how much is trying to maintain?
I try to get it all back. I just do resends. So like, there's all this stuff on being able to handle packet loss, which isn't really that useful for what I'm doing. It's really useful if you're doing an interactive like video chat with somebody.
Yeah.
But there you're talking about less than a third of second round trip time, and here my delays are like on the order of around 5 seconds.
Yeah.
Hopefully less, but could be around 5 seconds, and that gives you enough time to ask for a resend and things like that. So you have this failover time in the middle.
So I mean, there's a certain amount of model of accuracy you're looking for in television, which is that if you glitched a second or two, well, it's television.
Yeah, I appear to actually glitch a lot less than like YouTube does.
Okay.
Definitely a lot less than most streaming services do. It's actually really hard to get your glitching under control in general, so I'm very, very conservative about making it so that when you do get glitches, they're freezes, and then they happen very, very rarely. That you get a freeze, and then you don't get a freeze again for a really, really long time. Where other things will actually drop data and stuff. And I really, really try hard to never actually drop data. You always get the data, it just might be delayed a little bit. And you always get it on exactly the schedule that you should. Where other things try and play games where they get down to the wire and stuff. And I'm not doing that. I'm being a lot more conservative. Yes?
So, as I understand, I guess each peer needs to have about 10 times as much upstream bandwidth as
No.
the video's going to be? Or
No. Each peer should probably really have around, let's say, a third of the bit rate and upstream capacity. You can get away with less on individual peers, but they'll have constant churn. It's kind of annoying. The source should have 10 times. The source really should have 4 times, but it caps itself at 10 by default.
So,
I think right now it's capping itself at 20, but what?
Is that an amount that's practicable for a lot of if a lot of people are watching it on cell phones or something? Or is that a
cell phones are kind of a
can you be tolerant of
wireless net connections.
less bandwidth or-
Wireless net connections are kind of a problem. They behave really, really badly. In particular, they have crazy erratic ping times. I don't even know how they manage to pull that off, but they do. Like I don't like. Even if you have high loss, it doesn't cause high ping times. I do not know what they're doing to cause erratic ping times. That makes no sense to me.
They're doing low-level retransmission.
What?
Yeah.
They're doing low-level retransmission.
Oh.
They're trying to cover things up.
Oh. Okay. They should
see that.
They should stop doing
Stop
that.
saying evil. Yeah, I understand that.
They complain about us just as much.
Okay. All right. Fine. Anyway, so it only really works when you're on Wi-Fi or a reasonable net connection of some kind. I forgot where I was going with that.
I guess what I was leading to is
It
protocol work when some peers have less than that.
Oh, yeah. It does in fact have congestion
consumer
control.
only kind of.
It does in fact have congestion control. So in order for its in-club data, each peer needs some minimum amount of connectivity. In principle, if a peer discovered that it was really bad, it could just kind of not even do in-club. But it's rare for upload-download ratios to be so off that a peer that can't even handle that will actually be able to even watch the stream, so they tend to kick themselves out completely. But a peer will happily only do its in-club connectivity and have 0 out-of-club connections going out. And that will cause other peers to have more out-of-club connections going out.
You have to have out-of-club connections to receive 5/6 of the packets.
What?
But you have out-of-club connections to get.
Yeah, incoming you do, not outgoing. So each peer will have
Right, okay.
2 or 3 incoming and 2 or 3 outgoing in club. And then out of club, it'll have 5 incoming
Right.
and between 0 and infinity outgoing.
Okay, I see what you're saying.
And generally, fast peers have a lot of outgoing, and slow peers have many fewer. And that's how the congestion control works. And then it's very, very noisy. I bet a lot of firewalls would freak out about this really badly because it exhibits churn rates which are not supposed to happen in any known protocol. Yes?
Does this support like the video quality changing depending on the user's connection speed?
No.
So it's just whatever the broadcaster decides to broadcast.
Yeah,
at.
you can broadcast 2 different swarms at different bit rates, which is what tends to be done. In fact, even things like Justin.tv tend to just give you 2 options. And then if one kicks out, you, as the user, go, oh, I want the other one.
But that fragments the network, right? So then now you have half as many people sitting each.
Well, each peer brings its own upload capacity with its own download demand, so the fragmentation isn't really a problem or anything.
Okay, right.
Adds a little bit of requirements to the source in terms of having 2 things that it needs to source now. But it's not that big of a deal.